We are going to continue our work from the previous lesson. Here we want to graph the solution set for the linear inequality on a Cartesian plane. It's just written a little bit differently. What this is saying is it's saying that points x, y, so that fit this inequality. X subtract 2 is greater than 0, where x is an element of reals and y is an element of reals. That simply means that this is continuous data. Ultimately, what we have here is we've got x minus 2 greater than 0, and we want to graph this. So we solve for x. We are looking for the graph of the line x is greater than 2. If we go back to what the equality would be, this would be saying we have an x-intercept of 2. There is no y-coordinate, and if you think back to previous math classes, when you are left with just one variable, we are dealing with either a vertical or a horizontal line. And if we have an x-intercept here of 2, that means it must be a vertical line. Every point on this line has values of 2. So now the question, though, that you need to think about, so that was just to show you what kind of line we were going to have. But now to think about, is this going to be a dashed or a solid line? It's x greater than 2. There is no equal sign. So what we are dealing with is a dashed line. And now we need to determine whether or not we are going to shade to the left or to the right. Now common sense is going to tell you x greater than 2. Which direction do we go where x values are greater than 2? Well, to the right. We can prove this, though, using a test point. And let's say we choose 0, 0 as our test point. We have x minus 2 greater than 0. We substitute 0 in for the x, and we are left with negative 2 greater than 0. That is not a true statement, so we do not want to shade where our test point was. So yeah, we are shading to the right of the line. Discrete data are data that are consisting of separate or distinct parts. Discrete variables represent things that can be counted, such as people in a room. You cannot have parts of a person. So it is not possible to include all the data between 1 and 2 people. All right, so discrete is when we cannot include the in-between pieces. Now how we graph these is a little bit different. If it's discrete data, the solution region is what we call stippled. Really, all that means is it's a bunch of dots. And it's got to be dots on whole number parts. So we stipple the region. That's what this is called. Now, whether or not we simply stipple the boundary line, or whether we dash the boundary line, depends on whether or not there's an equality sign. If there is a greater than an equal or less than an equal, the boundary is simply stippled. So just like this example here to the left. But if the equality is not possible, so we've just got the less than or greater than, then the boundary is a dashed line. So that's like the example on the right. So in this one, we have points x and y such that they satisfy the inequality, negative 3y plus 6 greater than or equal to negative 6 plus y. Now in this case, we are told that we are dealing with integers. Integers are discrete data. So what we need to do is we need to have a stippled graph. Whether or not we have a dashed line remains to be seen. Is there an inequality with an equal sign here? The answer is yes, it's a greater than or equal to. That means everything is simply going to be stippled. In order to solve this, first of all, we need to rewrite this collecting like terms. So we might start by subtracting the y. So we'll have minus 4y plus 6 greater than or equal to negative 6. Subtract the 6, so we'll have negative 4y greater than or equal to negative 12. Divide both sides by negative 4, and recall, when you divide by a negative, you need to flip the inequality symbol around. So we are actually dealing with y less than or equal to 3. There's just the one variable, it's a y, so we have a horizontal line going through the point y equals 3. Remember, we said it's simply going to be stippled, not dashed, because there is an equality symbol, so these points are included in our region. So we stipple the line. Now what we need to determine is whether or not we are going to stipple above or below that line. And again, common sense is probably going to tell you if y needs to be less than 3, we are going to stipple below, but we can check by using a test point. And if we choose 0, 0 again, you're going to end up substituting 0 into the y. And is 0 less than or equal to 3? Yes, it is. So that means we want to shade our test point. So we need to stipple this whole region all the way below. And this gets to be fairly tedious with discrete data, but ultimately all of these points below the line should end up being stippled. All right, I'm not going to complete it, but I hope you get the picture. Everything below our boundary line will be stippled. How can you tell if the boundary of a linear inequality is vertical or horizontal without graphing the inequality? If you only end up with one variable, if there's just an x or just a y, we know it's going to be vertical or horizontal. If you end up with a y and then some value and a number, so it could be a greater than or equal to or whatever, if you end up with a y variable, we are dealing with a horizontal line. If you deal with an x variable, you are dealing with a vertical line. We want to determine the inequality for this graph. This is going to require you going back in mind to Math 10. All right, we can write the equation of a line using slope-intercept form. So if we think back to simply equations, y equals mx plus b. M represents the slope, b represents the y-intercept. The y-intercept happens to be 3. Slope is rise over run. Find 2 points that we do not have to approximate and do rise over run. We're going to go up, so we're going 1, 2, 3 up and 3 over. Rise over run, we went up 3, over 3, it's 1. So our slope is 1. So we have y equals 1x, or just x plus 3. Now what we need to determine is what inequality sign actually should go there. The equal sign needs to be replaced. We look at this. We have a dashed line for the boundary. Dashed line indicates it's going to be a less than or a greater than. There will be no equal to sign. Now we have to determine which one. You could take a guess, and maybe there's a fairly logical guess. We're shaded below. So maybe you say that the y values are going to be less than x plus 3. So you take a guess, logical guess, but then we can check it using a test point. Let's see if we were right. Does 0, 0 actually fit? 0 less than 0 plus 3. So 0 less than 3. Is 0 less than 3? Yes, it is. So then, therefore, we have chosen the correct inequality. So just to kind of summarize what we've done in the last 2 lessons. When a linear equality in 2 variables is represented graphically, its boundary divides the Cartesian plane into 2 half-planes. One of these half-planes represents the solution set of the linear inequality, which may or may not include points on the boundary itself. Things that you definitely need to know. To graph a linear inequality in two variables, follow these steps. Step 1, graph the boundary of the solution region. So you can either use the intercept method or you can use the slope-intercept method. If the linear inequality includes the possibility of the equal sign, so you've got the equal signs in there, and the solution set is continuous, we draw a solid line to show that all points on the boundaries are included. If the linear inequality includes the equal sign, but it's discrete data, you simply stipple the boundary. That means you simply put dots on it. If the linear inequality excludes the possibility of equality, so it's just less than or greater than, we use a dashed line. And it doesn't matter whether it's continuous or discrete, it is a dashed line. Step 2, choose a test point that is on one side of the boundary. We used 0, 0 every time, but you could use something else. So you substitute the coordinates of the test point into the linear inequality. As we stated, if possible, use 0, 0. It just simplifies your calculations. If the test point is a solution, shade the half plane that contains this point. Otherwise, shade the other half plane. So we have a whole bunch of examples. The first one on the left shows it was continuous data because they were both real numbers. There was an equal sign in the inequality. So it's a solid line, and then we are shading the entire half plane. In the second example, there was no equal sign, so it is a dashed line. Because they were real numbers, we shade the half plane. In the third example, there was an equal sign, but these were discrete data, so all we do is use dots along the line. And then we stipple the half plane. And in the last example, there was no equal sign as part of the inequality, so we use a dashed line. And because of the integers, then it is stippled. So when interpreting the solution region for a linear inequality, consider restrictions on the domain and range of the variable. This would apply to situational questions, which we haven't got into yet. But basically, if the solution set is continuous, all the points in the solution region are in the solution set. But if it's discrete data, only specific points in the solution are part of the solution set. And we represent this by stippling. Some solution sets may be restricted to specific quadrants. For example, most linear inequalities representing real-world problem situations have graphs that are restricted to the first quadrant. That means x is positive and y is positive.